This is what we were discussing at the end of class on Wednesday, where we had a circuit that looked something like this. Here's V in, here's V out. This is RS. And we had a small signal model that looked like this. Here's our gate. GM, VGS, VGS. As an optional thing, we might have some resistance R naught that we need to deal with. Here's our resistance R sub V. Here is our output voltage. Source to generation looks like this. And here is where our input voltage is applied. Okay, so we did the analysis last class meeting, and we found that neglecting channel length modulation, Rn is equal to infinity, and we found that R out was equal to RD. So the analysis that we wound up doing was correct. The output resistance should simply be RD when channel length modulation is neglected. So our last parameter then is to determine the voltage gain of our system. So to determine our voltage gain, I'm going to redraw our small signal model down here. Here's our gate. Here is our input voltage in. VGS. Here's our resistance RD. Here is our output voltage V out. And our voltage gain, as per usual, is simply the ratio of V out divided by V in. This guy is RS, and I'm going to label my terminals here. Okay. So, using Ohm's law, we can see that our output voltage, V out, is negative GM VGS multiplied by RD, because the current of GM VGS flows into the negative polarity terminal of RD and then flows out in its path around this loop. Okay. If we apply Kirchhoff's voltage law around the left-hand side of this loop, what we will find is that the quantity VGS is simply V in minus GM VGS times RS. So all I'm saying here is that this voltage drop VGS is more input voltage minus the voltage drop over our resistor RS. And doing a little bit of algebra here, this is going to look like VGS plus GM-RS VGS is equal to VN, which means VGS looks like VN divided by 1 plus GM-RS. So let's call this guy equation 1, this guy equation 2. What we're going to do now is simply substitute 2 into 1, which is going to give us V out is equal to negative GM times VN over 1 plus GM-RS times RD, which is the same as VN times negative GM-RD divided by 1 plus GM-RS. And from this, our voltage gain, V out over VN, is negative GM-RD divided by 1 plus GM-RS, which is the form that I prefer, because we can directly see how the gain of the device is affected by the effects of our source generation. But some textbooks choose to factor out GM from everything that they can, giving us negative RD divided by 1 over GM plus RS. This representation I actually like a little bit too, because effectively it's just a ratio of resistances that tells you what the voltage gain of this is, right? Where 1 over GM is a resistance, right? Because it's the inverse of a conductance. All right, so this is our voltage gain. Now, because we're dealing with CMOS, or excuse me, MOSFET circuits, we are going to be dealing with the effects of channel length modulation a lot. So I'm going to go ahead and derive our relationships with channel length modulation effects included as well, because that will make your life much, much easier when we get into 336. Okay, so our small signal model with channel length modulation included, or actually let's start here, including channel length modulation. Yes. Go back. We're good. All right. So let me draw our small signal model real quick, just to make my life slightly easier. Plus minus VGS, RS GM, VGS, RD like so. And while I'm at it, I'm going to make a copy of this guy. Okay. So to determine the quantity Rn, we would apply an input signal Vn here, determine a current In here, and the ratio of Vn to In should be our input resistance, right? That's our methodology for determining input resistance for literally any circuit. So by inspection, In is obviously 0, and therefore our input resistance Rn is Vn over In is the same as Vn over 0 amps. We have an infinitely large input impedance, which absolutely makes sense because what do we see when we look in an open circuit, right? Now let's look at R out. So to determine my output impedance, what I'm going to do is I'm going to short circuit my input terminals, and then I'm going to apply a voltage drop test here, and I'm going to measure this current I test. Now, if you went through my trash in my office, you would find that analyzing this thing can be a bit of a pain in the butt. So I formulated a way to do it in what I felt was a much more simple fashion. Okay. So what I'm going to do, I'm going to draw a dashed line right here. Okay. I'm going to disconnect everything to the left of the dashed line. And I'm going to find the Thevenin equivalent resistance of that left-hand network, right? Since everything to the left over here is a linear network, I am absolutely free to do that. That's the beauty of Thevenin and Norton equivalent circuits, right? I can replace any two-terminal linear network with a Thevenin equivalent representation. Since my network over here to the left only contains a dependent source and doesn't contain any independent sources, the expectation here is that it will be replaced by a single resistance, right? So let me redraw what we have to the left. I have my current source, GM, VGS, in parallel with my resistance R naught. At the bottom node, I have a resistor RS over which a voltage drop of VGS appears, having the following polarity. And then these are the terminals that I have representing where I disconnected the left-hand portion of the circuit from the right-hand portion of the circuit, right? So does anybody have any questions, comments, or concerns about how I've redrawn the left-hand side of this guy? Anything seem sketchy or anything? All right. So if I want the equivalent resistance network, I need to apply a test source method, right? Because it has a dependent source in it. So if I apply a test voltage, which in this case I'm going to call Vx, so it's not confusing since I already have a test source applied to my top network, I am now trying to determine this quantity Ix And the ratio of Vx to Ix will be the equivalent resistance of everything to the left of the dashed line. Are we okay with that? All right, so using Ohm's law, I can say that VGS is simply negative Ix times Rs, because all of this test current Ix splits and then recombines before it flows through that resistor Rs. If I apply Kirchhoff's voltage law to my right-hand loop, so this guy right here, I have Vx is equal to R naught times Ix minus GM VGS plus IXRS. So the voltage drop over my resistor R naught plus the voltage drop over my resistor RS sums together to give me the voltage drop Vx. Everybody okay with my application of KVL? So if I substitute in my relationship for VGS, what I get then is Vx is equal to R naught times Ix minus GM times negative Ix Rs, close parentheses or close brackets there, plus Ix times Rs, which looks like R naught times Ix plus GM Rs Ix plus Ix Rs. And from this, my Thevenin equivalent, Thevenin, I've been using capital T, capital H, right? Okay. Is Vx over Ix, which is just going to be R naught multiplied by 1 plus GMRS plus RS. So now what I'm going to do is I'm going to redraw this top circuit, but I'm going to replace everything to the left of the dashed line by that Thevenin equivalent resistance. So what that's going to look like is this. To be clear, here's my dashed line. Here's my quantity V test. Here's my current I test. So from this guy, I can easily see that my output resistance is just RD in parallel with the Thevenin equivalent of everything on the left-hand side. Or R naught times 1 plus GM RS plus RS, all in parallel with RD. Much less painless than doing it with everything in at the same time, which I actually don't know that I ever technically figured out how to do correctly.
I don't know why, that seems like really simple.
It is. I don't know why I didn't think about it the other day, because this is way easier than what I was trying to do.
Oh,
All right. Okay, so how do you guys feel about this?
Scared.
Scared? Terrified? Oh, that's not great. You guys learned Thevenin and Norton equivalent circuits way back in 221. So you've had literally 2 years of practice with it, or you're supposed to have had. Yeah. All right, well, you can watch my shitty YouTube channel to refresh yourselves on how Thevenin and Norton equivalent circuits. Or unfortunately, my YouTube channel is set up with my Louisiana Tech account, so I can't monetize it. So there's no way to bribe me for good grades. Oh no. All right.
There's no way to bribe you on that.
You know what? That's an interesting point, which we're not going to discuss any further. All right. So how do you guys feel about this output resistance relationship here? Everything seems reasonably straightforward.
That does make sense.
Okay. Wonderful. Now let's talk about our voltage gain relationship. All right, so I'm dropping this guy here. This is just the exact same small signal equivalent circuit. The only thing I'm going to do here is explicitly draw VN and V out. So I'm going to label a current here, and I'm going to call this current IX. And IX is the current that flows out of the positive polarity terminal of our resistor RD. So using Ohm's law, we can say that V out is equal to negative IX multiplied by RD. And I can rearrange this expression to find that IX is negative V out over RD, which I'm going to call equation 3, I believe. We all okay with this? Good old Ohm's law and a slight rearrangement. Okay. So if we apply Kirchhoff's voltage law to the left-hand path, so that means just around this loop containing the voltage VGS, what we will find is that our voltage VGS is equal to Vn minus Ix times RD, excuse me, RS, my apologies. And I can substitute in this relationship for Ix, which gives me VGS is equal to Vn plus RS times V out over RD. We all okay with the algebra? Let's call this guy 4. So what I'm going to do now is I'm going to apply Kirchhoff's voltage law around this right-hand loop. Let's put it right here. So that gives me V out is equal to the voltage drop over our resistor R naught, which is simply Ix minus GM VGS plus the voltage drop over resistor RS, which is Ix times RS. I'm going to substitute relationship 3 and relationship 4 into this expression where appropriate. which should give me an equation only in terms of V out, V in, and resistor values, effectively. So R naught times negative V out over RD minus GM times Vn plus RS times V out over RD plus RS times negative V out over RD is equal to V out. Checking the signs on all of my substitutions here. I don't see anything that's jumping out at me. All right, so now I'm going to just kind of expand things a little bit here, okay? So this is going to look like negative R naught times V out over RD minus GM R naught times Vn minus GM R naught times RS multiplied by V out over RD minus an RS times V out over RD. Are we okay with that? Expanded things out correctly. Okay, so I'm going to move all of these minus V out over RD terms from the right-hand side to the left-hand side. And so what that's going to look like is V out plus V out over RD multiplied by R naught plus RS plus GM R naught RS. And that will be equal to negative GM R naught. We all okay with that? Moving stuff from the right-hand side to the left-hand side? Anything wild or wacky? That was a loud noise. Okay. Yeah. So I'm now going to factor out VS from my left hand, or excuse me, V out from my left-hand side. And so that's going to look like V out times 1 plus R naught plus RS plus GM R naught RS. And all of this will be divided by the factor of RD. That will equal my right-hand side, negative GM R naught in. And then I'm going to make this ratio look a little bit better by replacing that 1 with RD over RD, which gives me R naught plus RS plus RD plus GM R naught RS divided by RD is equal to negative GM R naught Vn, and I can finally get my voltage gain. Voltage gain AV is given as V out divided by Vn. So that's going to be my right-hand coefficient, negative GM R naught, multiplied by the reciprocal of this fraction, right? So it's going to put an RD in my numerator. And then I'm going to have R naught plus RS plus RD plus GM R naught RS down here. This can be approximated as negative GM R naught RD divided by R naught times 1 plus GM RS, where effectively we're saying this term is much greater than individually RS and RD. When I ran a simulation, because I wanted to make sure I covered my ass thoroughly for this stuff after the embarrassment that was Wednesday's class. For the values that I chose, not including RS and RD, introduced a gain that was off only by a few hundredths. So the gain that I had with the full thing here was like negative 4.829. With this, it was negative 4.839. So not a huge amount of error introduced by using this simplification. As long as this guy, this product, is significantly larger than RS and RD, which should happen the overwhelming majority of the time, because our channel length modulation resistance are not usually on the order of several to tens of kiloohms, whereas RD is usually on the order of a few kiloohms and RS is usually on the order of several hundred ohms. So this approximation should be valid the overwhelming majority of the time. But if you're not comfortable, this is the exact solution. Luke.
Can you knock off the R or not?
Oh, I didn't even think about that. Sure. Yeah, you could. GMRD. Let's do that then. Well, actually, so that's interesting there. If we erase these, what is this expression? Go back like 2 pages in your notes. This is literally the gain of a source to generated common source amplifier without channel length modulation, which actually seems pretty reasonable that it should go to that, since R naught is larger than all the resistors in question. So I very much don't see a problem with this approximation now. It makes perfect sense.
So even with channel
About the same, yeah. And so let's talk about why that might make sense in a general sense, okay? So if your channel length modulation resistance R naught is much larger than your resistance RD, those two elements in parallel in our common source core amplifier are just going to look like something a little bit smaller than RD, right? Which means your gain would be negative GM times something a little bit smaller than RD. That's effectively what's happening here as well, except we have this emitter degeneration, excuse me, source degeneration term messing with our gain a little bit too. So yeah, seems reasonable. All right. So our last common source amplifier circuit that we are going to look at is the common source amplifier with a full bias network. All right, so this circuit will look something like this. And I'm going to give you the most convoluted possible version of this, so including signal resistances and all that kind of good stuff as well. I promise it's not going to be nearly as bad as you think. Here's our resistance RD. Here's where we take our output voltage V out. Here is our resistance RS. Here's a resistance R1. This is VDD. This is VDD. Here's our resistance R2. And then as an optional thing, we may choose to place a capacitor CS in parallel with our resistance RS. Donald, what does that capacitor CS do? So what does it look like at small signal?
So it's going to be an open circuit.
It's going to be an open circuit to DC. Short circuit to AC. Yeah, right. So if we include this source to generation capacitance effectively at AC frequencies, it shorts out this resistance RS, making this circuit look like a common source core to the right here. Let me put a dashed line here in the middle so that's obvious. Everything to the right of this dashed line looks like our common source core amplifier, or the most simple representation. And everything to the left looks like the voltage divider network, or the crap that we've been beating to death in this class for the last several weeks. So with a CS capacitor included, a simplified representation of this circuit would be this guy. Here's RD. Here's V out. And so I'm going to draw that dashed line again, because that is going to aid us in our analysis for determining input resistance, less so output resistance and voltage gain. Okay. So determining the quantity RA. If we look in here, directly at the gate terminal, what do we see?
It's like saying, oh.
Throw away the left-hand side. Look in your notes. Infinity. Okay. So between this node and ground, we see infinity. All right. So if we look in here, what do we see?
Parallel.
Exactly right. R sig plus R1 in parallel with R2 in parallel with infinity, which is just R sig plus R1 in parallel with R2. Does it matter whether or not we include channel length modulation? Not a little bit. So this is valid for both, right? With and without ELEN. Now let's look at the output resistance. I'm going to draw the small signal model for this guy to illustrate exactly what you probably think is going to happen. It's not going to have any effect on the output resistance when we attach resistance to the gate. So here's my gate terminal. Here's my source. GM, VGS. I'm going to draw this in red because we are going to see what happens with and without it. Here's my drain. This is RD. Over here are my output terminals, which we'll connect something there in a moment. This is VGS. This node is ground. Okay, so when we're determining our small signal equivalent between the gate terminal and ground, we have this parallel combination of R1 and R2 for sure. Here is our resistance R sig. And then this short circuit on the left-hand side is where our input voltage was going to be applied, right? But because we're measuring the output resistance, we short out the input voltage, okay? So here is our test voltage, V test. Here is our test current, I test. What do we see? What's VGS? So VGS is the voltage drop over this parallel resistance R1 and R2, also in parallel with that resistance R6. So what's the voltage drop over any of these three resistors on the left-hand side? It's zero, because there is nothing exciting this half of the circuit, right? Since VGS is zero, GM VGS is zero, right? So without channel length modulation, R out is simply RD. With channel length modulation, R out is R not in parallel with RD. Oops, and I didn't label R not, so I apologize for that. Let me put it in there. That might make things a little bit more obvious. Right? So when this guy is behaving like an open circuit, this current I test just splits between these two parallel resistances. So all we see is these two parallel resistances. Pardon?
I'm sorry.
Why did we drop RS? Okay, so with this degeneration capacitor in place, it effectively shorts RS, right? If this capacitance weren't here, what would this circuit be behaving like? Everything to the right of the dashed line. The one with source of generation, the one we just spent a significant portion of Wednesday's class and the first half of this class doing, right? Literally nothing different than what we've seen before. All right. Our last quantity to determine then is our voltage gain. Do I need to go back to the last page or? Sure.
Whenever we're like determining, you know, common source, common things, or like this and that, we're looking at it
Down further.
as an AC. Like we're looking at it as AC, so like our capacitors are already shorted.
Mm-hmm.
Okay.
Yes, so these circuits as an amplifier are what are called small signal amplifiers. So what we are doing in truth is we are perturbing the DC operating point by a little bit and seeing what comes out. Okay. So we have effectively an AC perturbation superimposed on top of our DC operating point. And we are analyzing these circuits right here, only looking at the small signal or AC representation. So we do our DC analysis. Let me scroll up here at the top. Our DC analysis would mean that these two capacitors look like open circuits, which means we effectively have a simple 4 resistor bias network for our MOSFET device, right? That we beat to death previous to exam 2, right? So the analysis to figure out the DC operating point, we have covered at length. What we're doing now is looking at the AC analysis where all of our DC terms are effectively 0, right? That's why we treat VDD as a small signal ground. We're turning off our DC sources. And so this capacitor right here at DC, it looks like an open circuit, which means that whatever our input signal is doesn't have any influence on any of the DC voltages in our bias network. Well, at AC, this guy looks like a short circuit so that we're applying our input signal and getting some perturbed output voltage that is actually superimposed on top of whatever that DC output voltage would be. Okay. So let's just say for the sake of argument that we have a 1 millivolt signal at our input and we have a gain of 10. Our output AC signal is going to be 10 millivolts, but that's going to be on top of whatever the DC value of VD, I guess is VD with respect to ground would be, right? So if we had this biased in such a way that our output voltage right here was, let's say 3 volts, it'll be a 3 volt constant term with a 10 millivolt ripple on top of it.
Okay.
When we get into 336, we're going to talk about how to get rid of that DC term from our output and all that kind of stuff, because I'm sure you guys have probably noticed for an op amp, which is based on transistor amplification, there is no DC portion of the output signal. If you put in an AC signal with a center, with no DC offset, you get out an AC signal with no DC offset. And this one, you put in an AC signal with no DC offset, you get out an AC signal with a DC offset because of the biasing conditions of the device. Okay. Does that clarify things?
A lot.
Okay, great. Voltage gain. So I'm going to look at this oral representation here again. Everything to the right of this dashed red line is an amplification stage. Everything to the left of the dashed red line is a voltage division stage. Okay. So if we call this voltage VG, the small signal gate voltage, I guess that technically should be lowercase g, but I'm too lazy to write it right now. Do we know what the relationship between VG and V out is? Yes.
So
Look at your notes.
the voltage at the gate with our small signal is gonna change our VGS, which is gonna change our descending current at the work, causing a negative gate across our output.
Okay, so what does that mean? Really want to help them out. When channeling modulation is included, you're absolutely correct. Okay, so all I'm saying here, again, let's throw away everything to the left of the dashed red line and treat this voltage VG as our input to this right-hand stage. So we have V in applied at the gate, V out taken at the drain. We don't have a source to generation resistor. We do have a resistance RD placed between the output and AC ground. This is just a common source core amplifier, which we know has a voltage gain of negative GM RD when channel length modulation is neglected, and it has a gain of negative GM R naught in parallel with RD when channel length modulation is included. Right? So the relationship between V out and VG is well defined based on our prior analysis. So I'm going to write that down. V out over VG is equal to negative GM R naught in parallel with RD, where when channel length modulation is neglected, R naught is infinity, and so this just simplifies to negative GM RD. Are we okay with that relationship? We can derive it again if we need to. All right. So for the voltage divider portion, we have something that looks like this. Here's our input voltage Vn. Here's our resistance R sig. Here is R1 in parallel with R2. Here's VG. So what we want to determine is effectively the transfer function of this voltage divider stage. VG over Vn. Logan, what's that going to be? Disagree. that would give us the drop over our SIG, not the drop over R1 in parallel with R2. So we got to put R1 in parallel with R2 in our numerators to get the voltage drop over that. R1 in parallel with R2 divided by R SIG plus R1 in parallel with R2. Okay. The voltage gain of the system is just these two transfer functions multiplied by each other, right? So AV is V out over VG multiplied by VG over VN, which gives us the V out over VN relationship that we're looking for. So this becomes negative GM1 R naught in parallel with RD multiplied by R1 in parallel with R2, all divided by R SIG plus R1 in parallel with R2. What the heck just happened? If our source to generation capacitor weren't here, what would we replace our V out over VG relationship with? So effectively, if this capacitor TS were not here, that would put that resistor RS in, and all of our details, it would do the exact same thing, except we would treat the right-hand side like a common source amplifier with limited generation. So when we got to the voltage gain, we would use those voltage gain relationships instead of the common source for voltage gain relationship.